Yeah. Hi, everyone. Thanks again for joining. And as Bhiksha said, this is the first lecture of a two-part series on GANs. The slides here are inspired by Ben, who used to take the lecture until last semester. So it's a lot of me repackaging his slides in a flow that's more natural to me. And I've added a few things of my own. So I just wanted to ask, is my cursor visible on
Yeah.
the screen that I've shared?
Yes.
Okay. So yeah, so I'd like to start with this quote by Anne LeCun, and he says that GANs and the variations are one of the most interesting ideas, or according to him, the most interesting ideas in ML in the last 10 years. GANs came out, or the first version of GANs came out in 2014. So it's not been that long. And to start off, I like to show a video that kind of shows what GANs can do, and we'll begin after that. So I'm not sure if the audio would be audible. Let, let me know if you cannot hear what's going on.
So pause it. You have to share the computer audio. So let me see. I think.
Is it
Malaria
audible right now?
Yeah. Yeah.
isn't just any disease. It's the deadliest disease there's ever been. Se dice que ha matado más de la mitad de la población que ha existido.
بليون من المتان مرض
وما زالت تقتل طفلا كل دقيقتين. Mais nous pouvons y mettre fin. Nous savons comment, nous en avons la possibilité. हमें और अधिक कार्रवाई की जरूरत है.
我们需要让世界领导人关注 hivyo tunazindua kampeni ya sauti. Omwele bawariopi malaria.
Speak up and say, malaria must die. One voice can be powerful, but all of our voices together, then they will have to listen.
Yeah, so as you guys probably saw, this was David Beckham speaking in 9 languages, and of course, he did not speak in all 9 of them. The voices were different as well. Some were male, some were female. So that was a hint of what GANs can do. Yeah, Obama in MIT, that's a good video as well. So with that, let's begin with GANs. This is a glimpse of what we'll do today. We'll touch on discriminative models, generative models, and then slowly get into GANs. So starting off, the original paper came out in 2014, and this did some interesting stuff with MNIST images, a bunch of faces, some scenic images. So they were in 2014, people were operating at a level of 28 cross 28, 32 cross 32 images. So MNIST is 28 cross 28. Then the faces, this is a CFAR data set, which is 32 cross 32. And slowly over the years, the image resolution has gotten better. The quality of images have gotten better. And around 2015, 2016, people started using convolutional neural networks with GANs. And that's kind of when, and a few other ideas. So before 2015 or 16, when the DC GAN paper came out, people were working with MLPs, feed for fully collected layers only in GANs. So that's so that kind of pushed through into getting images which were high resolution. And so here, I mean, the MNIST images look good, but there is not much content in MNIST images to be learned. Uh, the faces are not that good of a quality, and they're blurry, they're not clear. If you send these faces in your OPT application, it would probably get rejected because the faces are not clear. And people tried in the first couple of years to improve the quality of faces, and mostly also were dealing with how to improve scenic images, again dealing at a resolution of 32 cross 32, maybe 64 cross 64. A few variations of GANs came out around this time that worked on that. And slowly, over the years, the image quality has gotten better. And we'll go through the different architectures and the different variations in the second lecture that's on Wednesday. And with GANs, you can do a lot of other things as well. You can manipulate images and show emotions given an input image. So this is termed as image-to-image translation. And StarGAN was one of the papers that was able to do a multi-domain image-to-image translation with a single model. So that was the key thing about StarGAN. And slowly, again, the image resolutions have gotten better. The image quality has gotten better over the years, and GANs are now able to generate high quality natural images. GANs can generate pasta, mushrooms, rocket launches, fountains, and so on. So, starting off with meager digits, generating digits, MNIST digits, 28 cross 28. It's been a long journey for GANs and a very interesting one as well. So with that, I'll slowly get into GANs, touching on a few ideas along the way. The first thing we'll look at is discriminative and generative models and what's the difference between the two. So discriminative models, so given a distribution of our data X and the labels Y, in discriminative models, we're trying to learn the conditional distribution P of Y given X, whereas in generative models, we're trying to learn the joint distribution P of Y given X. So in discriminative models are in some sense learning the decision boundary between two classes of data, whereas generative models are actually learning the probability distribution of where the data comes from. And there are only limited things you can do with a discriminative model. You can use them for classification tasks, whereas generative models, you can do generative as well as discriminative classification tasks for them. And in some sense, generative models are a bit like learning a joint distribution is a harder problem than learning a conditional distribution. You need a deeper understanding of the data and the underlying distribution than you would for a discriminative model. And you guys must have studied a lot of discriminative versus generative models in a machine learning course that you might have taken even in this course. So maybe let me ask this: can anybody tell me a common discriminative model that they've studied in maybe an ML course? Very basic, simple discriminative model.
Sequence to sequence. Sequence to sequence.
Yeah, I mean, sequence to sequence. What about like a much simpler model that you like, the simplest discriminative model that you could have studied?
Naive Bayes.
A naive Bayes would probably, so it would come under the category of a generative model. You're learning in naive Bayes, you're learning the joint distribution of the data as well as the
Logistic
thing with naive,
regression.
yeah, logistic regression is a discriminative model. You are trying to learn a decision boundary. Support vector machines are another common discriminative model. A bunch of neural networks, they are discriminative models. Naive Bayes classifier is a generative model. You're learning the joint distribution there and then doing classification tasks using the Bayes rule. And GANS is, of course, a generative model as well, including VAE. Some other generative models you might have heard of are Gaussian mixture models, hidden Markov models. So, and something about explicit and implicit distributions as well. So these are two concepts that we'll uh, not need, but are important to keep in mind when we try to understand what GANs do. So GANs are generative models, and they're also implicit distribution models. So what's the difference between explicit and implicit distribution models? In an explicit distribution model, you'll calculate the probability of a data sample being from a particular distribution. So if you input, let's say in GANs, we'll be talking a lot about images. If you input an image into the model, it would give you, well, I see in the chat, which has written, yeah, garden variety of MLPs are also a bunch of discriminative models. So, but yeah, explicit distribution models, what they'll give you is the probability of that data point being from a particular distribution. Whereas in an implicit distribution model, what it does is it will generate a data point from a particular distribution without explicitly modeling that distribution. So GANs come under the category of implicit distribution models. They are a generative model. And yeah, so before I move on, any questions on generative models and implicit and explicit distribution models? Right. Let me check the chat.
Is VAE an implicit distribution model?
Yeah. So in VAEs, as we'll see in the next slide, we're not modeling explicitly the distributions. We're training. So let's look at VAEs. So in VAEs, what we're trying to do is we're trying to train the decoder to be able to generate images from a chosen prior distribution. And this is usually unit normal Gaussian distribution. And we're training the encoder to to map the distribution of where the data is coming from to our chosen prior distribution. So we're not learning, right? Yeah. So you cannot, as Victor said, you cannot compute P of X for any given X. So it is, yeah, you cannot do that with VAs. So yeah, what we're trying to do here is train our decoder to generate images from a latent vector space of our choice. And the encoder tries to minimize the KL divergence between the input distribution and our chosen distribution. And there are certain key differences. There are certain key differences between VAs and GANs. And one of them is that in VAs, we're trying to minimize the KL divergence between two distributions. And in GANs, as we'll see, we're trying to minimize the Jensen-Shannon divergence between the two distributions. And the difference between the two isn't much. We'll come across the derivation of GANs and see what Jensen-Shannon divergence is, and again touch upon that next Wednesday, so this Wednesday. In VAs, we're trying to minimize the bound on the divergence, on the KL divergence between the generated and the target distribution, which is the variation lower bound. And in GANs, we're minimizing the actual divergence between the generated and the target distribution. So these are two key differences. The optimization problems in VAs is a simpler optimization. It trains faster, more reliably, but even though the results are a bit blurry. GANs, on the other hand, they're difficult to optimize. There are a bunch of training issues, as we'll see. the divergence in some sense is noisy. But if you're able to do it with a bit of tricks, some of these tricks do not have a lot of theoretical backing, but it's as they say, it's more of an art than a science. You end up usually with sharper results than with VAs. So with that, I'd like to slowly get into GANs gently. But does anyone have any questions up to this point? Because now we'll start with GANs and what they do.
So is GAN explicitly generative model?
GAN is a generative model, yes.
Is it an explicit generative model?
No, it's an implicit generative model. It's you're not modeling the distribution again, but you're learning to sample from that distribution.
Got it, thank you.
So I see a question in chat. Can you explain the second bullet point under VAs? So, well, it goes back to the VA lecture. What we start off is that we want to minimize the KL divergence between a chosen prior distribution and P of Z given X. And that's, we do a bunch of math, and what we end up deciding is, okay, minimizing the KL divergence is same as working with the lower bound or the variation lower bound of that. So it's, I would say it's go back and look at, if you go back and look at the derivation of how VAs do, it's something that is a step in VAs. Okay, so with that, let's dive into what GANs are. So GANs are generative adversarial networks. So the generative aspect of them is, again, we try to learn from the underlying distribution from which our data set comes from. And something that we know does that is a VAE. The adversarial component comes from the adversarial training that we do in GANs. There are two competing networks in GANs who are, in some sense, adversaries of each other. They're trying to beat each other at a game. And in this competition, we end up with a generative model that is able to do the task which we wanted to do, which is to generate from the underlying distribution from which our data set comes from. And the networks part is, of course, that they're made of neural networks. The aim here we can think of is to generate data from an unlabeled data that's given to us. So we have a data set which we don't necessarily have labels for that data set. And we want a model that understands the distribution from which our data set is coming from. And when needed, when called upon, generate or sample from that distribution to generate new images, new data points from the same distribution that our data comes from. When I'll be talking about data, mostly in GANs, I'll take the example of images. They are easier to show, and you don't have to listen to audios every time I talk about a data point. But yeah, we'll do an exercise here. So hopefully the point I want to come across here is that GANs are quite intuitive. Like what I feel is, so what we'll do here is we'll try and come up with the GAN architecture and the training process on our own, discussing with each other. And the point, and I feel like if I would give this kind of a problem statement, half of you would probably come up with the GAN architecture, and the other half would probably come up with something better. And that's not to say that what they did was very trivial, but what I want to say is that the GAN architecture and the training is very beautiful. It's very intuitive. And that's the point that I want to bring across. So essentially what we're doing in GANs is, let's say I want to teach someone to do a task. I would tell that person that, okay, I want you to do this. I want you to do X task. And that person has never done that task before. They have no practice, no understanding of what they have to do. So they'll do a very bad job at it. And that's what basically our generator is. It's the person who has to do a task that I tell it to do. What goes inside the generator is a random vector from a vector space that we've chosen. It's usually a unit normal Gaussian distribution. The dimensionality of the space is a hyperparameter. You can choose whatever dimensional space you want. It's a zero mean unit variance Gaussian. That latent vector goes inside the generator. And what comes out is the generated data. It's analogous to that I've asked a person to do a task. And now with no experience of doing a certain task, it'll do a very bad job at it. Now, when I look at what the person has done, I expected something to be done, and there's something that was done by them. There is a difference between my expectations of the task and what was done. And I want to, in some sense, so what I do is I tell them the difference between my expectation and what was expected out of them, and they learn from that information. Now, only if there was a way that I could propagate my expectations into the generator, and the generator could use that expectation to update its weight. But we have the next best thing. What we have in GANs is another neural network called the discriminator. And it is doing exactly what I said. It is looking at the job done by the generator. It has certain expectations from what job should be ideally. And it, in some sense, quantifies how bad the generator was. And it back propagates that expectation. And the generator uses that information to update itself, to learn, to get better at the task. And the task, again, is to generate data from the same distribution that our data comes from. So the discriminator is another neural network that is able to differentiate between real data and fake data. Now, what's real and fake data? Real data, by definition, is the data set that's given to us. The data that we have, we call it real data by definition. And anything that's generated by the generator, we call it fake data. So, and these are the two components that are present in GANs. The generator, who is trying to do the task for us of generating from the same distribution that our data is coming from, and the discriminator, whose task it is to differentiate, to tell how good or bad of a job the generator did, and also quantify that goodness or badness, which the generator can take and learn. So with that, let's see how we can train again. So this is the situation that we have at time t equal to 0. We have a generator, which is a neural network that's randomly initialized. So it's good at nothing. It takes in a latent vector, again, from a vector space that we've chosen. It generates an image. And initially at time t equal to 0, because the weights are randomly initialized, it's the generator is no good. It'll generate some gibberish. And the discriminator is the second component of GANs, and it's trained, or so what it can do, its capability is that it can differentiate between generated data and the given training data that we have. And again, real data is a class name given to our data set. Fake data is the class name given to the data that's generated from the generator. So a question here is, what kind of a neural network do you think the discriminator would be? You've studied these kinds of neural networks. Right, Zichen says CNN plus MLP, yes, definitely. But what would you, so yeah, that's what the neural network will be made of, CNNs and MLPs. But what would its job be? How would you describe the network? Yeah, so I have a response called classification, exactly. And not just a classifier, exactly. It will be a binary classifier. That's what a discriminator is. It differentiates between two classes of data: fake data, which by definition is anything that's generated from the generator; real data, which by definition is our data set. Now I want to train a GAN, and I have two components, the generator and the discriminator. Now, which of these two components should I train first? So Vivek says generator. So why do you think we should train the generator first?
So that the discriminator has both the classes and it can discriminate between them, or can give a feedback towards the generator.
Yeah, but the thing here is that the generator, what does it mean to train the generator? I think what you mean is that we want the generator to produce something so that there is some data that the discriminator can use to train. But like the entire idea of the generator learning revolves around a feedback that comes from the discriminator. So if there is no feedback coming from the discriminator, then essentially you cannot train the generator. So basically the first network that we want to train, the first component in GANS that we want to train is the discriminator, because without a guide which the discriminator is for the generator, without that beacon of light in the generator's life, the generator cannot learn. And so the first component that we train in GANS is always the discriminator. But with what training data? I guess that was touching on what Vivek was saying, is that how do we get the training data that we use to train the discriminator? Yeah, Zichen says generate random matrices. Yeah, so in some sense, yes. So the discriminator is a binary classifier. Again, two classes, real and fake. Real by definition is our data set. But we don't generate random matrices. What we do is we generate data from the generator. So we input random vectors, as we said, that go in the generator. And we generate whatever images that the generator is currently able to produce. So at time t equal to 0, it's randomly initialized. So it'll produce a bunch of gibberish. And that's okay. By definition, that data comes in the fake class. And that's the data that we use in the fake class, and in the real class we use the actual our given data set. And these things now produce the data set that we can use to train the generator, the discriminator. And again, the first network that we train is the discriminator. Now, what's next? We've trained the discriminator once. Sorry. So we trained the discriminator once. Now our job is to train the generator. But what's our training object. We know that training the discriminator, it's a binary classification problem, binary cross entropy loss, and the training is done. We know where the data is coming from. Now we have to train the generator, but what do you guys think would be our training objective when we train the generator?
So I think if the discriminator is able to realize that it's a fake image from the generator, then the generator will incur a penalty. And if it is able to realize that it is a true image from the generator, then probably generator will be doing a good job, I guess.
Yeah, exactly. And I see a bunch of correct answers in the chat as well, but that's exactly what it is. We want to generate images from the generator such that they're classified incorrectly by the discriminator. So as Tushar said, if the images are classified incorrectly by the discriminator, there is no penalty to the generator. If not, then the generator incurs some penalty. And that's the information that we encode in the generator loss function. So, and that's it. That's how we train GANs. We start off with training the discriminator with the current ability of the generator. And by current ability, I mean whatever the generator can produce. If the generator is initially initialized randomly, then it will produce a bunch of gibberish, and that's okay. That's our training data for the generator. And then in the step 2, we train the generator to beat the discriminator, to fool the discriminator, to make the discriminator predict what it produced incorrectly, so that the discriminator predicts the data coming from the generator as being coming from a real class rather than the fake class. And again, we generate images such that they're classified incorrectly by the discriminator. And that's what we do in that's just what we keep doing until we find that the generator is now doing its job. So that's how we train a GAN. And I hope it was intuitive to all of you. And yeah, so next we'll get into theory behind GANs, a little bit of math. But I hope this was good intuition. And at this point, I'd like to stop for any questions that you may have. So yeah, let me know. Yes, so there's a question in chat. Are we going to talk about the generator's loss function later? Yes, we're going to talk about loss functions later. So what do you mean by not trained? So there's a question in chat. They're not trained simultaneously, right? What do you mean by simultaneously? Yeah, so there's a good question in chat. When do we switch between training the discriminator and the generator? Is it on the epoch when the loss plateaus for every n training instances? There is no like, at least there is no theoretical justification to what the right answer is. What we do in practice are different things. We sometimes train the discriminator for one epoch and the generator for one epoch, or we train the discriminator a little more so that the discriminator is is trained optimally to guide the generator. We also it's there. So this is in some sense an adversarial balance that is the issue with training GANs. You don't want to overtrain the discriminator, because if you overtrain the discriminator, the gradients would be too sharp and the generator would not be able to learn. But if you don't train the discriminator enough, then the discriminator would be a bad teacher, so it does not know its stuff, and then again the generator would have a hard time to be able to learn. And this is in some sense the issue with training GANs. It's a balance that you have to strike. There are different architectures and different things people do, and this is something we'll touch on and speak about in on Wednesday, as to what's the right balance and what are the different things people do, and why is it that if we train the discriminator like too much, then it's the generator is not learning anything, or there'll just be oscillations and they'll never reach an optimum stationary point that they're supposed to reach. And this balance exactly is what makes training GANs tricky, is to find the right balance of how much to train each of the two components. Yeah, so in terms of trained simultaneously, yeah, they're not trained simultaneously as like both being trained together. We train the discriminator first and then use that, what the current state of the discriminator we have, to train the generator. Now, it's again, so that's why it's an adversarial training, and it's also described as a two-player game where our first player is the discriminator. It trains to do the job. Now the generator now is training or learning to beat the discriminator. Now the generator has now leveled up, and then so now the discriminator also has to level up. So then we train the discriminator with the data that the generator generated. And remember, now that generator is not generating gibberish, it's gotten better. So the discriminator levels up, we train it again with the current ability of the generator again. So whatever that current ability is. And we keep doing that in loops until we are satisfied with what the generator is doing. When the discriminator classifies everything perfectly, then we train the generator. Ideally, we want the perfect discriminator. But again, as I said, we don't want to overtrain the discriminator. We don't want the discriminator to be absolutely confident so that there are no gradients at all for anything that's coming from the generator. And but we also don't want the discriminator to be really inaccurate, so that it's not it's a binary classification problem, and if it's not working at very high accuracies, that's a problem as well. So the question is, when the discriminator classifies everything perfectly, then we train the generator. Yeah, but then it depends on what you mean by perfectly, and that's exactly the question of the training balance that I was talking about. Yeah, there are a lot of heuristics, a lot of training practices that we should follow in GANs, and we look at a bunch of them in the next lecture, which will touch on different GAN architectures, why they do what they do, different training practices that people use. All right, so with that, let's get into some math. And who doesn't love math? So starting off, just a brief review. GANs were introduced in 2014. The goal is to model PFX distribution of our training data, but GANs don't actually do that. GANs learn to generate samples from PFX. So that's the implicit distribution modeling idea that GANs do. And they're trained using a pair of, so there are the two components in GANs are are adversaries, and they compete with each other basically. The generator learns the probability distribution P of X of Z. Z is a latent vector, which is sampled from a known prior, such as a Gaussian. X is our data, the data that we have. And the generator we can think of as a mapping between the latent vector space to the vector space that our data is coming from, but also mapping between the latent distribution to the data distribution that we have. And the goal here is that the generated distribution G of Z matches the true distribution P of X. The discriminator, on the other hand, is trained to tell the difference between the real and the generated data. And its job is to backpropagate its expectations to the generator. And that's all that the discriminator does. It's kind of thrown away after the generator is trained. So its purpose in life is to train the generator, it's to provide feedback to the generator. And once that's done, it has served its purpose. So people have used it for other tasks, but in at least the vanilla implementation of GANS, the discriminator is discarded once the generator is trained. So this is what the original GAN formulation looks like. Originally GANs were formulated in the form of a min-max game. So DX. So here there are certain notational subtleties that you should take care of, and I'll try and highlight them as best as I can. D here is D of X is basically the input that's generated by the discriminator. What the discriminator wants is to generate a 1 for real data and to generate a 0 for anything that comes out of the generator. G of Z is the output produced by the generator. And what the generator wants is to make the discriminator output 1 for whatever it produced. So that's kind of the game that the two networks are playing. Sorry. So yeah, and this is the objective that we're working with. The discriminator is trying to maximize this objective. So what the discriminator wants is to maximize the log likelihood of the output, given that the input is the real data, and what the generator wants is to minimize the again this objective, and what it wants is that the discriminator outputs a 1 for whatever was produced from the generator. And so like you can see, if the discriminator produces a 1 for input for what was generated from the generator, it's a log of 0, which is going to be minus infinity, which minimizes the objective function. Whereas if that's not the case, then we are trying to maximize the objective function. And again, they're at odds with each other, the discriminator and the generator, and in some sense are trying to do opposite things. So with that, let's try and derive what an optimal discriminator looks like. And this is a bit of math here, and I'd like to highlight certain things in the notation. So P of D, the D here, corresponds to the actual data distribution. So when you look at these equations, the notations are a little poorly chosen, and it was partly laziness on my part that I didn't change it. But the D here corresponds to the actual data distribution, whereas the capital D here inside the log likelihood, it's the output of the discriminator. So don't confuse between the two Ds. PD is the data distribution. PG is the generated data distribution, is the distribution that the generator generates. And DX is the discriminator output. So again, our objective function is this. And what we want to do here is to find out what an optimal discriminator does. And to do that, we fix a generator that we have. So we say that we have a generator and that remains fixed. Given a generator, what would be our optimal discriminator? And to do that, to find that, we are now, you want to optimize this objective function. The thing to note here is, okay, and this these expectations can be written like this. So what we've done here is now, over here in this equation, in some sense, X represented a data point from our data set. But in this equation, we've replaced G of Z by X. And what X is representing is it's a general point in the vector space from which our data came from, but it's a general point. It could belong to our data distribution. It could belong to another distribution. It's a general point. So if we're talking about, say, MNIST images, which are 28 cross 28, X in this equation is a point from that 784 dimensional vector space. And the only thing here is now that what goes inside the first expectation is supposed to be the real data. So X here is distributed according to the real data distribution, the actual data distribution, and X in this expectation value is distributed according to the generated data distribution. So it's the same thing that we do here, but the meaning of X has kind of changed. Here, X was what we meant by X was that it's the real data and we take the expectation over the real data. And here Z was a latent vector space, and the G of Z was something that the generator produced. Here, the meaning of X has in some sense shifted, but again, what goes in the first expectation value is X being distributed according to the actual data distribution, and here X is distributed according to the generated data distribution. And once that's clear, the entire derivation would be like a breeze because there's nothing much after this. So if anyone has any questions up to this point, I'll be happy to answer, because once we're done with that, then it's going to be real simple to understand what's next.
I have a question about, can you explain in the high level sense why the objective looks like expectation of X times log D plus expectation of Z times log 1 minus D? Because I don't think I understand why the equation is this form.
Okay. So let's maybe I'll show. So I want to annotate. Yeah, I can. Can you see my annotations?
Yes, we can.
Okay, so it's exactly goes back to what we discussed when we were trying to create an intuition for what was going on. So Z is something that we choose from. We choose from a chosen prior latent space. Now G of Z is the output that's produced by the generator. D of G of Z is the output that's produced by the discriminator given the input comes from the generator. Now, ideally, what we want the generator output to do from the point of view of the generator is to produce a 1 here. So if this happens, then the generator has done its job. And if this is happening, then 1 minus d of g of z would be in some sense 0. So you can understand d of g of z as being the probability of the fake data in some sense. So if this is 0, that means that the job of the generator is done. And if this is, and that's why we say that the generator is trying to minimize this objective. And if this is 1, so if the entire thing is 0, that means d of g of z is 1. But if the entire thing is 1, that means that this is 0, and that means the job of the generator is not done at all. But that is where this 1 minus d g of z comes from. I think this is a little counterintuitive in some sense, but this portion is basically just saying that the discriminator, we want to maximize the log likelihood of the real data being classified as real by the discriminator. So you can understand dx as being the probability that x belongs to the real class, and 1 minus d g of z as being the probability of the fake data. So we want the generator to maximize the probability of the fake data in some sense. I don't know if that helped, but I think if this is very, it's not that hard if you like break it down into the simplest of steps and do it yourself. It would be pretty evident as to why this is the formulation. This is what the objective function for GANS look like, and why we're doing this.
Akshat, may I?
Yeah.
So d of x is the probability that d of x is the probability of authenticness that the discriminator assigns. And so 1 minus d is the probability of fakeness that the discriminator assigns. So when you say expected value with over x of d log d of x, you want, this is the expected value of the probability of authenticness for data, for real data. So you want this to be maximized because you always want the real data to be called authentic. And expected value over z of log of 1 minus d is, this is the expected value over synthetic data of the log of the probability that the discriminator calls it synthetic. And so you, on synthetic data, you want the discriminator to call it synthetic. So you want that term maximized, the second term. On real data, you want the discriminator to call it authentic. So you want that first term also to be maximized. Does that make sense? No, I guess go ahead, Akshat, sorry. So what if the fake data were in some sense closer to real data, but not exactly real data? So the fake data are fake, period, right? They cannot be closer to real data than real data itself.
Yeah, what if the fake data is in some sense closer to the real data, but not exactly the real data? Do we get 0 for d of g of z? So if the fake data is closer to the real data, then the output from the discriminator should be closer to 1. And that's what we want the discriminator in some sense. We want the generator to make the discriminator do that. If the real data and the fake data are close together, then the output of, so this value should be closer to 1. And in some sense, again, we're minimizing the this expectation.
Can I ask one more follow-up question? Is can you explain the min max in front of the V on the objective? Like, why do you, I understand max D, I think, but like min G, what does it mean?
Well, it's just meaning that the aim of from the perspective of the generator is to minimize this objective V. That's all it means. So the same way the discriminator wants to maximize this objective, the generator wants to minimize this objective function.
Okay, thank you.
Okay, so I guess let's move on in interest of time. So just to reiterate what I was saying here, X is the real distribution, a point from the actual data distribution. Here, X is a general point in the vector space of our images. So if it's an MNIST image, it's a 784 dimensional space. But this expectation is taken over a distribution distributed according to the actual data distribution. This distribution is taken over, this expectation is taken over distribution distributed with the generated data distribution. If we expand this into this expectations in the form of an integral, this is what it looks like. Again, the probability distribution here is the actual data distribution. The probability distribution here is the generated data distribution, which has like a one-to-one correspondence with the loss function. So here we're looking at the real data distribution, and in this term we're looking at the generated data distribution. We take the derivative with respect to the discriminator to find the optimal discriminator, and this is like doing a bunch of math, rearranging these terms. This is the expression that we get, that the discriminator output is the ratio. So given a data point from that vector space that corresponds to our images, the discriminator, what the discriminator outputs is the ratio of the probability of that data point from being the actual data distribution divided by the sum of the probability of that data point from being from the generated data distribution plus the actual data distribution. So here it's I like to highlight the difference between explicit and implicit distribution modeling. If you were doing an explicit distribution modeling, we'd be finding the expressions of each of these probabilities, so each of these things, but that's not what we're doing. In GANS, it's an implicit distribution model, and that's why what we don't need to find is these explicit terms, but it's enough to just output this ratio and our job is done. So this is the expression for an optimal discriminator given a particular generator. And hopefully like the questions that people had about the loss functions get cleared up in the next couple of slides. Wait, so, all right. So again, let's look at two cases here. So d of x, that's the output that our discriminator is supposed to give. And let's say we have a bad generator. Now, how I would translate a bad generator in words is that there is no way that the output of the generator looks like my data. So x in no way would look like the actual data that I have. So in that scenario, probability of d, probability of x belonging to the actual data distribution would be 0. The probability of x coming from our generated data would obviously be 1, and the discriminator would output a 0. That's the case of a bad generator where it's not doing its job nicely, basically. And again, if you put that back into the loss function, you get that the objective function is in some sense minimized. Okay, so and case 2, here we have a good generator. And that is something I'll translate into words as I cannot tell the difference between the output of the generator and my data. So what do you think the output of the discriminator would be in that case?
One for the one, I guess.
Yeah, I mean, so P of D of X would be 1. The probability of X coming from the actual distribution would be 1 because it's a good generator. It's generating points that are similar to our actual distribution, but so would P of G of X. So the output of the discriminator would be 0.5 in this case. So that was the optimal discriminator. What it's doing is outputting the ratio of the probability of a point belonging to the actual distribution by the sum of the probability of a point belonging to the actual and the generated distribution. Now let's look at what the optimal generator would look like. And again, it's going back to our intuition as to first we trained the discriminator, we found the optimal discriminator. Now we want to find what the generator is doing according to this objective function, given that we have an optimal discriminator. So to do that in this expression, we put in the expression of an optimal discriminator. And what this ends up being, this looks similar to KL divergence, but it's what this term is called the Jensen-Shannon divergence. And this is what the generator wants to minimize. So let me define a Jensen-Shannon divergence. If you want to find the Jensen-Shannon divergence between two distributions, P of T and P of G, then the Jensen-Shannon divergence is the sum of the KL divergences between P of T, and M here corresponds to the average of the two distributions. And this is in some sense the expression for the Jensen-Shannon divergence. And so what the optimal generator here is doing, it's minimizing the Jensen-Shannon divergence between the actual data distribution and what is generated by the distribution. So it's I mean, you can think of it in terms of KL divergence as well. There are certain properties of GST that are a little different from KL divergence, which we'll look into on Wednesday. But that's kind of what it comes down to, that, okay, we find an optimal discriminator, and given an optimal discriminator, what is it that our generator is doing? If we look at the given loss function according to the given objective that we're trying to minimize, it's trying to minimize the divergence between the real data or our data, actual data, and the generated distribution. And that's kind of exactly what we want, right? That's what we want our generator to do. We want our generator to make whatever it's producing be as similar as possible to the real data distribution. So that, in some sense, completes the proof of the fact that the generator and the discriminator and the GANs in general are actually doing what we're expecting them to do, what our intuition told them we would do. So a few questions in the chat. Yeah, it's the GS diversion is calculating the KLD of two distributions against their average. It's true. It's symmetric. As Viksha said, there are a couple of other properties that Jensen-Shannon divergence has over KL divergence that we'll probably get into on Wednesday. But to summarize, what's going on in GANS is that, again, the the thing to note from all this math is that there exists a stationary point, and if the generated data exactly matches the real data, the discriminator outputs 0.5 for all inputs. And if that's the case, then the generator does not learn. There is no need for the generator to learn. It's kind of done its job. And that's the stable point that we want to reach from, and that's kind of the objective that we want to reach in GANS. It's difficult to do. And the idea here is that the stationary point exists, but it need not be stable. And that's what kind of makes the training of GANs to be hard. An example that I think is good to describe this situation is like if you take the example of a pencil and you want to stabilize it on its peak. If you do that on its peak, a stationary point exists, but it's quite unstable, and just a little tilt to the left or the right would make the system collapse. And that's kind of similar to what we have in GANs. The stationary points exist, but it's not stable. And that's going back to the adversarial balance that we have. We don't want, because we have two adversaries, we don't want one to overtrain, because if that happens, the system kind of, it could go into oscillation and never reach the stationary point. And there are a bunch of other things that go on in GANs, and we'll look at them on Wednesday. But to summarize again, both the generator and the discriminator be training in this min-max optimization simultaneously, but simultaneously means in some sense one after the other and not in the same epoch. And if the discriminator is undertrained, it provides a suboptimal feedback to the generator. If the discriminator is overtrained, there is no local feedback for marginal improvements. And hence we need to train the discriminator and the generator together. The discriminator needs to be trained on the current ability of the generator, and the generator needs to be trained so that it beats the current version of the discriminator. So that was basically the math of GANs. I'll stop for some questions. I see a few in the chat. Zijan says, do we want to reach the min-max stationary point through training or avoid that? No, we want to reach that point. I'm not sure I get the question. Why would we want to avoid that? So stationary point, okay, my slides are stuck.
I'm just wondering whether our objective will allow you to reach that point, and do we want to reach the stationary point because the generator will become so good at the point, right?
Sorry, didn't catch the last part. The generator would be
quite good at generating.
Yeah, exactly, and it would be able to fool the discriminator, as we talked about. The output would be 0.5, and that means that the real distribution and the generated distribution are exactly the same, and that's ideally the point that we want to reach. I see.
I guess it can also mean that the discriminator is undertrained.
Yeah, but yeah, I mean, like, at least theoretically what we're talking about is, I mean, remember, we're talking about an optimal discriminator. So if we have an optimal discriminator, what the generator is doing is minimizing the Jensen-Shannon divergence. If it's a new divergence metric, just don't worry about the name, but we're minimizing the divergence between two distributions. And that's only happening if we have an optimal discriminator. So theoretically, we're always reaching the optimal point. So theoretically, we don't have a scenario where our discriminator is undertrained. That's something that happens in practice, what you said.
So when you said in the next slide, you mentioned that the stationary point might need not be stable. So I'm guessing that means we can reach the point, but would still be able to train the network through the point because it's not stable.
Yeah, I mean, there are possibilities of overshooting. there are possibilities of never reaching that point. And it kind of boils down to two-player games. I'd say I'll highlight these issues myself in the next lecture. I'll show you why they can happen, where they can happen, and what we're doing to kind of avoid these situations. But yeah, you're right. We could train through the stationary point. Is there a typo? Right. Yeah. So do you mean, yeah. Yeah. So someone just pointed out a typo here. This should have been like two lines, which are basically signifying the distance.
And also
Yeah,
the Jensen channel has PG plus PG in the denominator. One of them should be PB.
Oh yeah, here. I'm sorry. Yeah, it should be. Oh yeah, I'm so sorry. It should be PG plus PD. Yeah, sorry about that.
We'll fix those. We'll fix those into the back.
Yeah. So I want to cover GAN evaluations, but there is a question as to what I mean by local feedback. Where? Yeah, so it basically corresponds to something we do in practice. A local feedback would be that the cross entropy, so the softmax output are basically if the discriminator is too confident about its predictions, the cross entropy values in some sense would be very high, and that provides little feedback for marginal improvements. It's something quite. So I'd say it's an obvious thing. If you look at the outputs of the softmax from the discriminator, you can think of them as being, say, 0.99 and 0.01. And if the discriminator is kind of overconfident about everything, then it's hard to learn from that kind of a feedback. But if the values vary a little bit, then even there is a possibility of marginal improvements. That's kind of what I meant by local feedback. There is no like very deep meaning about that. It was more of an intuitive thing from an implementation point of view. So finally, so the one final thing I want to cover is GANS evaluation and how do we evaluate GANS. And there is, so this is one, sorry, there is no objective metric as such to evaluate GANs. The ideal way would be to get humans to make sure that the images that are being generated by the generator resemble the actual data distribution. So if we have MNIST images as our actual data distribution, we want that those images correspond to or look like digits, and we can get a bunch of people to sit down and make sure that that's the case. That's a very expensive way of evaluating, and that's something we prefer not to do every time we write a GAN paper, but that is the ideal way to do it. There are other ways that people have come up with approximating the test set likelihood. It's in some sense what our generator is doing is sampling from a particular distribution, and if it corresponds to the real data distribution, then the likelihood of it generating an image that looks like our data set, our actual data set, is higher than the likelihood of an image from a distribution that's far away from our real distribution to do that. So that's something that we can do here. The way to do it is like, say, sample 1 million images from the generated data distribution and how many of our test set images are one of those generated images. And that's another way to do it. One, ideally we'd want some human to be able to do it, but we're finding ways around that. Another way to do it is using a discriminative network to evaluate GANs, and inception scores are one of the most popular ways to do it. And here what we're doing is doing evaluation through a discriminative network. And the discriminative network we used, or the people who came up with this metric originally used, was the inception v3 architecture, from which we get the name. So the inception model worked on, was trained on ImageNet. It had 1,000 classes. So what we want the generator to do is to produce a variety of labels. So another common thing that is observed in GANs is the phenomenon of mode collapse. What happens in mode collapse is that, let's say we want to generate data for MNIST data set, which has 10 digits. So there are 10 different classes for which you want to generate data, but what the generator will do is now the distribution learned somehow focuses only on one digit. So it's either producing just all ones or all threes. And that's why we kind of want a variety in the labels that are produced by the generator, or the labels that are given to the images produced by the generator through the inception architecture. We also want that each label should have high confidence, which kind of tells us that the images are closer to that particular class that's predicted by the architecture. And both these components are in some sense taken into account in calculating the inception score. And yeah, that's one of the more popular ways of evaluating GANs and how the generator is doing. So that's it for this lecture. A little preview of what will happen on Wednesday. We'll go through certain training issues in GANs, look at some GAN architectures, GAN training and stabilization techniques. We look at Wasserstein GAN, and if there is still time, we'll look at super resolution with GANs. So that was it for this lecture. That's all I wanted to cover. We're close to time, and I'll stay back for any questions that you might have. But thank you guys for attending.
Can you explain the expression for, there's no page number. So it is on the page where you wrote down the Jensen-Shannon divergence expression. Yeah, just now. Yeah,
this
here.
one? Yeah.
Yes, can you explain on the second line at the F equals expectation of PD log something. So how did you go from the log dx to the fraction there?
Right. So if we look at, so once again, if we go a few slides back, we derived this expression for an optimal discriminator, right? So what we do is we put this in over there. So we take this expression for the optimal discriminator, and we plug this in here. That's all that's done here. There is a typo here. It should be PD and PD, but that's all that we do. So again, what we're doing, the aim here is to find the optimal generator, given that we have an optimal discriminator that we found before.
How about the log 4? Where did it come from?
How about what?
Negative log 4.
Oh, so that's so I mean, we'd have to do the math, but I can give a hint of where it comes from. So do you see this 2? And that would kind of translate to log 4. So if you do it, it's very trivial, but this too is the source of that log4.
Okay, thanks.
Yeah, thank you.
So thank you, everybody. I'll stop the recording and you can continue.